Right now, somewhere in this universe, a star 30 times the mass of our Sun is about to die. And when it does, it won't just fade away quietly. In less than 1 second, its core will collapse so violently that it punches a hole in the fabric of reality itself. A region where gravity is so extreme that space curves in on itself, time slows to a crawl, and anything, absolutely anything, that crosses a certain invisible boundary will never come back. Not light, not information, not even the laws of physics as we understand them. That is a black hole. And here's the thing that keeps me up at night. We used to think these were rare, exotic curiosities tucked away in the most extreme corners of the cosmos. We were wrong. There could be 40 quintillion of them out there. That's a 4 followed by 19 zeros. And they are not just sitting quietly in the dark. They are building galaxies, devouring stars, bending time, and as of this year, revealing secrets we never imagined possible. So, let's go on a journey. From the moment a black hole was nothing more than an embarrassing mistake in Einstein's math, all the way to the cutting-edge discoveries of 2026 that are genuinely rewriting what we know. And I promise you, by the end, the way you look at the night sky will never quite be the same. Let's start at the beginning. And I don't mean the beginning of black holes. I mean the beginning of us even imagining they could exist. Because for a long time, nobody wanted them to be real. The year is 1783. An English clergyman named John Michell writes a letter to the Royal Society, and in it, he proposes something that sounds almost ridiculous. He suggests that a star 500 times the mass of our Sun would have gravity so powerful that even light could not escape it. He calls it a dark star. And then, for over a century, the entire scientific world basically shrugs and moves on. Fast forward to 1915. Albert Einstein publishes his theory of general relativity, this beautiful framework that reimagines gravity not as a force, but as a curvature in space-time caused by mass. It was revolutionary. It was elegant. And buried inside the mathematics was something Einstein himself did not want to find. Just 1 year later, a German astronomer named Carl Schwarzschild, while actually serving on the front lines of World War I, solves Einstein's equations for a single concentrated mass. And what falls out of the math is terrifying. There is a radius, a boundary, beyond which gravity becomes so overwhelming that nothing, not matter, not energy, not light, can ever climb back out. Schwarzschild dies just months later, never knowing that he had described the anatomy of a black hole. But here's the part that I find genuinely fascinating. Einstein hated it. In 1935, he published a paper saying, and I'm paraphrasing here, that singularities bring so much chaos into the theory that they basically cancel out the laws of physics. And then, in 1939, he went even further, publishing a paper explicitly arguing that black holes were impossible. He believed some unknown force would prevent a star from collapsing that far. And on the exact same day, September 1st, 1939, the very same day that Nazi Germany invaded Poland and World War II began, a physicist named J. Robert Oppenheimer published a paper proving Einstein wrong. Oppenheimer showed mathematically that a massive star absolutely will collapse completely, punching through that Schwarzschild radius and forming what we would later call a black hole. But because the world was, understandably, a bit distracted that day, the paper was basically forgotten for 20 years. Think about that. The moment we proved black holes were inevitable was the same moment the world descended into its darkest chapter. Oppenheimer's paper sat in obscurity while he went on to build the atomic bomb. The universe has a strange sense of timing. Now, the name black hole did not even exist until 1967, when the physicist John Wheeler finally coined the term during a lecture. Before that, scientists called them frozen stars, or gravitationally completely collapsed objects. You can see why the catchier name stuck. And it wasn't until 1971 that we actually found one. Cygnus X1, a system about 7,200 light-years from Earth, where a blue supergiant star orbits an invisible companion roughly 21 times the mass of our Sun. The first confirmed black hole, and the subject of a famous bet. Stephen Hawking wagered against its existence. He called it an insurance policy. If black holes turned out not to be real, at least he'd win the bet. He conceded in 1990. But here's a question that should make you pause. If black holes are born from dying stars, then what about the very beginning? What about the Big Bang? See, when the universe was less than a second old, it was unimaginably dense. Every particle in existence crammed into a space smaller than an atom. And in 1966, Soviet physicists Yakov Zeldovich and Igor Novikov proposed something wild. They suggested that in those first fractions of a second, some pockets of matter were so concentrated that they collapsed directly into black holes without ever forming a star at all. Stephen Hawking expanded on this idea in 1971. These are called primordial black holes, and they could range in size from the mass of an asteroid to the mass of a moon. For decades, this was just a theory, a beautiful, elegant, but completely unproven theory. And then something happened. On November 12, 2025, LIGO, the gravitational wave observatory that spans 2 sites across the United States, detected a signal. It was catalogued as S251112cm. And when scientists analyzed it, they found something that stopped them cold. At least one of the objects involved in this collision weighed less than a single solar mass. Now, here's why that matters. No known process in the universe can create a black hole that small from a dying star. The physics simply doesn't allow it. There's a hard limit, called the Chandrasekhar limit, at about 1.4 solar masses. Below that, a star just doesn't have enough mass to collapse into a black hole. So, if this object really was a black hole, and the evidence is very strong that it was, then it could only have formed one way. In the first moments after the Big Bang, before stars, before atoms, before the universe as we know it even existed. Nico Cappelluti from the University of Miami put it plainly when he said, "We believe our study will aid in confirming that primordial black holes actually do exist." And it gets even stranger. In 2023, a detector called KM3NET, an underwater telescope in the Mediterranean Sea, captured a neutrino with an energy level that should have been impossible. About 100,000 times more powerful than anything the Large Hadron Collider has ever produced. 35 times more energetic than any neutrino ever detected before. And there's no known source in the universe that can create that kind of energy. But physicists at MIT and the University of Massachusetts Amherst proposed an explanation that gave the entire field goosebumps. That neutrino, they said, may have come from a primordial black hole in its final moments of existence, exploding in a burst of something called Hawking radiation. David Kaiser at MIT described it perfectly. He said, "You'll never, ever hope to see Hawking radiation if the only black holes ever were ones that formed from dead stars." Primordial black holes have different masses and different lifetimes. Some go bang right now. If this is confirmed and the research is ongoing, it would be the first experimental evidence of Hawking radiation, the first direct proof that primordial black holes exist, and potentially an explanation for dark matter, all from a single particle hitting a detector at the bottom of the sea. That's three of the biggest open questions in physics, potentially answered by one ghost particle. But let's come back to the black holes we know best, the ones born from stars. When a star at least 20 to 25 times the mass of our Sun exhausts its nuclear fuel, the outward pressure that kept it inflated for millions of years simply vanishes. And in less than a second, the core collapses. The outer layers are blown off in a supernova, one of the most energetic events in the universe. And what remains, if the core is heavy enough, becomes a black hole. Now, what does a black hole actually do to the universe around it? Because they don't just sit there. This year, astronomers measured something nobody had ever measured before. Using 18 years of radio data from a planet-sized network of telescopes, a team led by Steve Prabhu tracked the jets erupting from Cygnus X1, that very first black hole we ever confirmed. And they found that those jets carry the energy of 10,000 suns and travel at roughly half the speed of light, 355 million miles per hour. And 10% of all the energy released as matter falls toward the black hole, gets channeled directly into those jets. Think about that. A region of space smaller than a city, generating as much energy as 10,000 stars and firing it across light years like a cosmic fire hose. And then there's Galaxy J, 1007 plus 3, 540, where a supermassive black hole at the galaxy's core went silent for nearly 100 million years, just dormant, sleeping. And then it woke up. New jets erupted, stretching nearly 1 million light-years across space, slamming into the surrounding galaxy cluster like a cosmic volcano. 100 million years of silence, followed by an explosion that spans distances our minds can barely comprehend. But perhaps the most disturbing thing a black hole can do is eat. When a star wanders too close, the difference in gravitational pull between the near side and the far side literally stretches it into long, thin strands, a process scientists actually call spaghettification. The star is pulled apart like taffy, its material spiraling into a superheated disk that can outshine entire galaxies. We call this a tidal disruption event. And earlier this year, astronomers observed one where the black hole kept ejecting material for years after the star was destroyed. Years. As if the black hole was still burping from a meal it finished long ago. Now, here's where it gets philosophically unsettling. What is actually inside a black hole? According to Einstein's equations, at the very center is something called a singularity, a point where all the mass is compressed to zero volume and infinite density. A place where the laws of physics, every equation we've ever written, break down completely. It's not a place in space. It's more like a moment in time. Once you cross the event horizon, the singularity is not ahead of you in the way a wall is ahead of you in a room. It is in your future. You cannot avoid it any more than you can avoid next Tuesday. But most physicists suspect the singularity is a sign that our theory is incomplete, that when we finally figure out how to merge gravity with quantum mechanics, the singularity will dissolve into something else. Maybe a Planck star, an incredibly dense but finite object predicted by loop quantum gravity. Maybe a fuzzball, a tangled knot of quantum strings predicted by string theory. Nobody knows yet. And that beautiful, maddening uncertainty is part of what makes black holes so captivating. And there's another puzzle. Hawking showed in 1974 that black holes are not actually eternal. They slowly radiate energy and lose mass through a quantum process now called Hawking radiation. A black hole the mass of our Sun would take roughly 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. The universe itself is only about 13.8 billion years old, so we're talking timescales that make the age of the cosmos look like a blink. But here's the heartbreaking part. That radiation appears to be random. It seems to carry no information about what fell in. And quantum mechanics insists that information can never be destroyed. So either quantum mechanics is wrong, or general relativity is wrong. Or there's something deeper going on that we haven't figured out yet. This is called the black hole information paradox, and it remains one of the deepest unsolved problems in all of physics. Even Hawking himself conceded in 2004 that information is probably preserved, but we still don't know how. And just when you thought it couldn't get more mind-bending, 2026 delivered one more revelation that genuinely shook the field. A team of researchers published a study in the monthly notices of the Royal Astronomical Society, arguing that Sagittarius A star, the 4 million solar mass object we've been calling the supermassive black hole at the center of our galaxy, might not be a black hole at all. They propose it could be an ultra-dense clump of dark matter made of lightweight particles called fermions, forming a compact core that mimics a black hole's gravitational effects so perfectly that even the famous Event Horizon Telescope image is consistent with their model. Valentina Crespi, the lead author, said the dense dark matter core could bend light so strongly that it creates a central darkness surrounded by a bright ring. Exactly what we photographed. Now, this is not yet the consensus view. It's a provocative alternative supported by new data from the European Space Agency's Gaia mission. But it raises a question that honestly gives me chills. What if the thing we've been staring at for decades, the object we built an Earth-sized telescope to photograph, isn't what we thought it was? What if the boundary between what we know and what we only think we know is thinner than we imagined? And maybe that's the most important thing about black holes. They are not just objects in the sky. They are mirrors for our ignorance. Every time we think we've understood them, they reveal another layer of mystery. They were predicted by equations their creator didn't believe. They were proven inevitable by a paper nobody read. They were named by a man who initially doubted them. And now, in 2026, they're being redefined by signals from the very first moments of the universe. We are alive during the single most exciting era in the history of black hole science. The era when we went from imagining them to photographing them, from theorizing about their radiation to potentially detecting it, from assuming they were simple to discovering they might hold the key to dark matter, quantum gravity, and the origin of the universe itself. And every time you look up at the night sky, Just know that scattered among those points of light are regions where space-time has folded in on itself so completely that not even the universe can see what's inside. Pockets of infinite mystery hiding in plain sight. If this video made you look at the cosmos a little differently, I'd love it if you subscribed to the channel. Drop a comment telling me which discovery from this video surprised you the most. Was it the possible primordial black hole signal? The neutrino from an exploding black hole? Or the idea that Sagittarius A star might not be a black hole at all? And if you know someone who'd love this, send it their way. I'll see you in the next one. Right now, somewhere in the Milky Way, a star that has been burning for millions of years is about to just disappear. No explosion, no supernova, no fireworks. It will simply collapse in on itself and vanish from the universe, leaving behind something so dense, so gravitationally extreme that not even light can escape it. And here is the wild part. We actually watched this happen. For the first time in history, astronomers caught a star in the act of silently becoming a black hole. And that is just one type of black hole. Because as it turns out, these cosmic monsters come in very different flavors. From ones forged in the death throes of giant stars, to ones born in the first fraction of a second after the Big Bang itself, to ones sitting right at the center of our galaxy that might not even be a black hole at all. So today, we are going to break down every single type of black hole that scientists have discovered, theorized, and in some cases, just detected for the very first time. And I promise you, by the end of this, the way you think about the universe is going to be fundamentally different. Let us start at the beginning, because the story of black holes is honestly one of the strangest chapters in all of science. The idea that something could have gravity so strong that light itself could not escape goes all the way back to 1783, when a British thinker named John Michell wrote a letter describing what he called a dark star. But the real math did not show up until 1915, when Albert Einstein published his general theory of relativity. And here is where it gets beautifully ironic. Just months later, a German physicist named Karl Schwarzschild, who was literally serving on the Russian front during World War I, solved Einstein's equations and found something disturbing hidden inside them. There was a critical radius around any mass, where if you compressed matter small enough, gravity would become so overwhelming that nothing could ever leave. Einstein received Schwarzschild's letter from the trenches, and you know what his reaction was. He thought it was mathematically interesting, but physically impossible. Einstein, the man whose own theory predicted black holes, spent the next 2 decades arguing they could never actually form. Arthur Eddington, one of the most brilliant astrophysicists of the early 20th century, famously declared, "There should be a law of nature to prevent a star from behaving in this absurd way." Well, the universe did not care about their opinions. The first type of black hole we need to talk about is the one that forms when massive stars die, and these are called stellar mass black holes. They are the most common type, and they are everywhere. Astronomers estimate our Milky Way galaxy alone contains somewhere between 10 million and 1 billion of them. Let that sink in. Up to 1 billion black holes just in our galaxy. Here is how they form. A star that is at least about 8 to 10 times the mass of our Sun spends millions of years fusing hydrogen into helium in its core, and that fusion creates outward pressure that perfectly balances the crushing inward force of gravity. It is a beautiful cosmic tug-of-war. But eventually, the star runs out of fuel. And when that happens, gravity wins. The core collapses catastrophically, and in many cases, this triggers a supernova, one of the most violent explosions in the universe. What is left behind if the core is massive enough is a black hole. Typically, these range from about 3 to around 100 times the mass of our Sun. The most famous example is Cygnus X1, which holds a very special place in history. It was discovered back in 1964 when a pair of Geiger counters were launched on a rocket from New Mexico and picked up an incredibly powerful X-ray source in the constellation Cygnus. It took almost a decade before astronomers confirmed what it really was. In 1972, 3 scientists working independently, Charles Thomas Bolton, Louise Webster, and Paul Murdin, identified it as the first strong black hole candidate. And even then, the debate raged on. Stephen Hawking famously made a bet with physicist Kip Thorne in 1974 that Cygnus X1 was not actually a black hole. He called it insurance. If black holes did not exist, at least he would win the bet. He conceded in 1990. Today we know Cygnus X1 intimately. It sits about 7,200 light-years from Earth. It has a mass of about 21 times our Sun, and it is locked in a 5.6-day orbit with a blue supergiant companion star, roughly 40 times the Sun's mass. And just this month, in April 2026, researchers published something remarkable in Nature Astronomy. Using 18 years of radio telescope data from a planet-spanning network, they measured the power of Cygnus X1's jets for the first time ever. Those jets are blasting out energy equivalent to 10,000 suns. They literally watched the jets dancing, being bent and pushed by the companion star's wind as the black hole orbited. It is the first time we have measured the instantaneous power of a stellar black hole's jets, and it confirms theories about how black holes shape the space around them. But here is where the story of stellar black holes got turned on its head. In February 2026, a paper published in Science described something that had been hiding in plain sight for over 5 years. A star in the Andromeda Galaxy, 2.5 million light-years away, designated M31-2014-D S1, had been a massive red supergiant, about 13 times the mass of our Sun. In 2014, NASA telescopes noticed it getting brighter in infrared light. It glowed for about 3 years, and then it just faded away, disappeared. No supernova, no explosion, nothing. The lead researcher, Kishalay D. from Columbia University, said something that honestly gave me chills. He said, quote, "It comes as a shock to know that a massive star basically disappeared and died without an explosion, and nobody noticed it for more than 5 years. What happened was a failed supernova. The star's core collapsed, but the shockwave was too weak to blow the outer layers off. Instead, nearly everything fell inward and formed a black hole. The outer layers were gently pushed away as a shell of dust, and the star simply ceased to exist." This was the most detailed observation ever of a star making that transition, and it fundamentally changes our understanding of how stellar black holes are born. We always assumed stars of this mass would explode. Turns out, some of them just go quietly into the dark. Now let us go much, much bigger. Because while stellar mass black holes are impressive, they are tiny compared to the monsters lurking at the centers of galaxies. Supermassive black holes are, without exaggeration, the most extreme objects in the known universe. We are talking about black holes with masses ranging from hundreds of thousands to billions of times the mass of our Sun. And they sit at the hearts of most, if not all, massive galaxies. Our own Milky Way has one. It is called Sagittarius A star, and it weighs in at about 4.3 million solar masses. It sits roughly 26,000 light-years from Earth, and in May 2022, the Event Horizon Telescope gave us the first image of its shadow. But Sagittarius, our star, is actually modest compared to the real titans out there. The black hole at the center of galaxy Messier 87, the one that gave us the very first black hole image back in April 2019, is about 6.5 billion solar masses. Billion, with a B. But here is the thing that keeps astrophysicists up at night. How did these monsters get so big, so fast? Because the James Webb Space Telescope has been finding supermassive black holes existing when the universe was less than 1 billion years old. And our standard models simply cannot explain how they grew that enormous in such a short amount of time. This is what scientists call the too big, too fast problem. And 2026 has been an absolutely wild year for cracking it open. In January, a study published in Nature solved one of Webb's biggest mysteries. You know, those strange little red dots that kept showing up in the telescope's deep field images. Hundreds of them, scattered across the earliest epochs of the universe, glowing red and then vanishing about 1 billion years later. Researchers at the Cosmic Dawn Center in Copenhagen figured out what they are. They are young, supermassive black holes wrapped in dense cocoons of ionized gas. And here is the kicker. They are about 100 times less massive than previous estimates suggested, with masses between 100,000 and 10 million times the Sun. Professor Darach Watson, one of the lead researchers, explained that these are baby supermassive black holes caught in the middle of their growth spurt, gorging on the gas surrounding them. The heat generated by this feeding frenzy shines through the cocoon and creates that distinctive red glow. This finding, published on the front page of Nature, tells us we are watching the origin story of supermassive black holes in real time. And if you thought that was mind-bending, also in January 2026, a team from Waseda University found a quasar at a distance of about 12 billion years in the past that was feeding at 13 times the Eddington limit. That is 13 times the theoretical speed limit for how fast a black hole can consume matter. At this rate, radiation pressure from the infalling material should push everything away and stop the feeding. But this black hole was not only gorging beyond its limit, it was simultaneously blasting out powerful X-ray emissions and launching a radio jet. According to most models, those three things should not be happening at the same time. It suggests we are catching a black hole during a brief, unstable, transitional growth spurt that our current physics cannot fully explain. And then, just this April, a supermassive black hole in a galaxy called J1007+3540 woke up after being dormant for nearly 100 million years and erupted like a cosmic volcano. Fresh jets blasted outward, creating distorted structures stretching nearly 1 million light-years across. Meanwhile, in galaxy V-Val 340a, astronomers found the largest stream of superheated gas ever observed flowing from a galaxy, stretching 20,000 light-years from the center, driven by a precessing, wobbling black hole jet shaped like a giant S. The universe's supermassive black holes are not just sitting there. They are alive, active, and reshaping entire galaxies. All right, now we enter the realm of the mysterious. Because between stellar mass black holes, which top out around 100 solar masses, and supermassive black holes, which start at hundreds of thousands, there is a gap, a huge, puzzling gap. And this is where intermediate mass black holes live, or where they should live. Because finding them has been one of the biggest challenges in modern astrophysics. Intermediate mass black holes range from roughly 100 to 100,000 solar masses. They are the missing link. If supermassive black holes grew from smaller ones over billions of years through mergers, then intermediate mass black holes should exist as a transitional phase. The problem is, there is no common natural process that easily makes a black hole of this size. Stars do not get big enough to collapse directly into one, and merging enough stellar mass black holes takes an incredibly long time. But we are finally finding them. The strongest candidate sits in Omega Centauri, the largest and brightest globular cluster visible from Earth. Using over 500 Hubble images spanning 20 years and cataloguing the motions of 1.4 million stars, astronomers discovered 7 stars in the cluster's core that should not be there. They are moving so fast, they should have escaped the cluster entirely. The best explanation is an intermediate mass black hole of at least 8,200 solar masses pulling them in. It sits just 17,700 light-years from Earth, actually closer to us than Sagittarius A star. And then came the gravitational wave bombshell. In November 2023, LIGO detected a signal designated GW231123, and when they analyzed it, the results were staggering. 2 black holes, roughly 100 and 140 times the mass of the Sun, had smashed together to create a monster of 225 solar masses. This is the most massive black hole merger ever detected. But what made it truly extraordinary is that both of those original black holes fall in or near what physicists call the forbidden mass range, between about 60 and 130 solar masses, a process called pair instability. Supernova should completely destroy a star, leaving no remnant at all. No black hole, nothing. These black holes should not exist, unless they were not born from stars at all, but were themselves products of earlier mergers. Black holes merging with black holes, growing step by step, hierarchical mergers. And these two were spinning near the maximum rate allowed by Einstein's theory of relativity, about 4 million times the rotation rate of Earth. We are watching black holes evolve, generation by generation, like a cosmic family tree. Now for the type that could change everything. The one that, if confirmed, would rewrite textbooks and solve one of the biggest mysteries in all of cosmology. I am talking about primordial black holes. Every other type of black hole we have discussed forms from stuff that already exists in the universe. Stars, gas clouds, mergers. But primordial black holes are different. They would have formed in the first fraction of a second after the Big Bang itself, born from density fluctuations in the incredibly hot, dense soup of the infant universe. No star required. The idea was first proposed by Soviet scientists Yakov Zeldovich and Igor Novikov in the 1960s, and Stephen Hawking further developed it in the 1970s. But for decades, primordial black holes remained purely theoretical, until possibly now. On November 12, 2025, LIGO detected a gravitational wave signal catalogued as S251112cm. And when researchers analyzed it, they found something that stopped them cold. The collision involved at least one object with a mass less than that of our Sun. Let me explain why that is such a big deal. The minimum mass for a black hole formed from a dying star is about 1.4 solar masses. That is a hard physical limit. No known stellar process can create a black hole lighter than that. But this signal showed an object between 10 and 87% of the Sun's mass. Too heavy to be anything normal, too light to be a stellar black hole. Two researchers at the University of Miami, Associate Professor Nico Cappelluti and PhD student Alberto Magaraggia, built a framework to explain what LIGO might have found. Their conclusion, published in early 2026 and headed for the Astrophysical Journal, is that the most plausible explanation is a primordial black hole born in the earliest moments of cosmic history. They estimated how many primordial black holes LIGO should be able to detect and found that the rarity of this signal is actually exactly what you would expect. It is rare because primordial black holes themselves should be rare. And here is the part that could reshape our entire understanding of the cosmos. If primordial black holes exist in sufficient numbers, they could account for a significant portion or even all of dark matter. Dark matter makes up about 85% of all matter in the universe. We know it is there because of its gravitational effects, but we have never directly detected it. If dark matter is not some exotic undiscovered particle, but rather billions of tiny black holes forged in the first fraction of a second after the Big Bang, that changes everything. Now, I need to be honest with you. This is not confirmed yet. Some scientists think the signal could be noise in LIGO's detectors, and there is an alternative interpretation involving a subsolar mass neutron star merger. Cappelluti himself has said they will need to detect another such signal, or even several, for smoking gun confirmation. But the tools are improving rapidly, and the math fits. We might be standing at the edge of one of the most profound discoveries in the history of astrophysics. There is one more type we need to talk about, and it is both the newest and possibly the most important for understanding how the universe built itself. These are called direct collapse black holes. Remember the too big, too fast problem? How supermassive black holes appeared when the universe was less than 1 billion years old. Well, there are two competing theories. The light seed theory says you start small, with stellar mass black holes, and grow through mergers over billions of years. But that takes too long to explain what Webb is seeing. The heavy seed theory, the one behind direct collapse black holes, says something much more dramatic happened. In the very early universe, under specific primordial conditions, pristine clouds of gas did not fragment into stars. Instead, they collapsed wholesale, directly into black holes of 100,000 to 1 million solar masses. You skip the star phase entirely. You just go straight from a gas cloud to a massive black hole. In 2025, the James Webb Space Telescope found what might be exactly this. In a system nicknamed the Infinity Galaxy, where two spiral galaxies are colliding, Webb detected a 1 million solar mass black hole embedded in ionized gas between the two galaxy nuclei. And the system also has 2 additional active supermassive black holes in each galaxy's core, making it a triple black hole system. Peter van Dokkum from Yale, who led the study, was careful to note they cannot say definitively they found a direct collapse black hole. But the data strengthens the case while eliminating competing explanations. And I saved the most mind-bending twist for last. What if the object at the center of our galaxy, the thing we have been calling Sagittarius a star for decades, the object Reinhard Genzel and Andrea Ghez won a Nobel Prize for identifying, what if it is not actually a black hole? In February 2026, a team led by Valentina Crespi at the Institute of Astrophysics La Plata in Argentina published a study in the monthly notices of the Royal Astronomical Society proposing something radical. They suggest that Sagittarius A star could instead be an ultra-compact core of dark matter made of particles called fermions. And before you dismiss this, listen to what their model can do. It reproduces the orbits of the S-stars, those stars that whip around the galactic center at speeds up to 30,000 kilometers per second, roughly 10% the speed of light. It matches the orbits of the dust-shrouded G-sources near the center. It is consistent with the famous shadow image captured by the Event Horizon Telescope. And when combined with the latest data from the European Space Agency's Gaia mission, it explains the Milky Way's rotation curve at vast distances. Their co-author Carlos Argüelles put it beautifully. He said, "We are not just replacing the black hole with a dark object. We are proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance." Now, the researchers themselves are the first to say this is not necessarily more probable than the black hole explanation. The EHT's founding director, Shep Doeleman at Harvard, has pointed out that observed magnetic field patterns near the event horizon are particularly consistent with black hole properties. And fermionic dark matter cores have a theoretical mass limit of about 10 million solar masses, which does not explain how you would get a 6.5 billion solar mass object like M87 star. We need better data. But the fact that we cannot currently distinguish between these two scenarios at the center of our own galaxy, that is humbling. So let us step back and take in the full picture. We live in a universe where dying stars silently collapse into black holes without even a whisper, where monsters millions and billions of times the mass of our sun anchor entire galaxies and reshape them with jets spanning 1 million light-years. Where missing link black holes are being assembled through cosmic collisions, generation after generation. Where objects born in the first heartbeat of the Big Bang might be lurking invisibly all around us, possibly making up most of the matter in the cosmos. Where gas clouds may have skipped straight to becoming black holes without bothering with stars first. And where the very definition of what sits at the center of our galaxy is still up for debate. We went from Albert Einstein insisting black holes were impossible to Karl Schwarzschild solving the math from a World War I battlefield, to Stephen Hawking making bets about whether they were real, to literally photographing one, all in about a century. And now, in 2026, we are watching stars collapse into them live, detecting their primordial cousins for the first time, and questioning whether the most famous one of all might be something even stranger than we imagined. The universe is not just stranger than we suppose. It is stranger than we can suppose. And the story of black holes is nowhere close to being finished. If this video blew your mind even a fraction as much as researching it blew mine, hit subscribe because we cover discoveries like this every single week. Drop a comment telling me which type of black hole fascinates you the most. Is it the silent stellar collapses, the primordial ones that could explain dark matter? Or is it the possibility that Sagittarius A star might not be a black hole at all? I genuinely want to know. And if you have a friend who loves space, send them this video. I guarantee it will start a conversation.
Right now, as you watch this, the universe is doing something that no scientist on Earth can explain. Not because the equipment is broken, not because we have not looked hard enough, but because the more we look, the stranger it gets. We live in an age where we can photograph a black hole 55 million light years away. We have sent probes beyond our own solar system. We have mapped the human genome. And yet, some of the most fundamental questions about reality, about the cosmos, about your own mind, remain completely unanswered. These are not fringe theories. These are not the kind of things you find at the bottom of a conspiracy website. These are real, documented, peer-reviewed mysteries that are actively driving some of the greatest scientific minds in history to the edge of what they know. And in 2026, they are no closer to cracking them. So buckle in, because what you are about to hear is going to change how you see everything. Let us start with something that should not be possible. On the 16th of March 2025, a telescope in British Columbia detected something extraordinary. A flash of radio waves from deep space. That alone is not unusual. What made this one different was that it was the single brightest fast radio burst ever recorded in human history. Scientists nicknamed it RB Float, which stands for Radio Brightest Flash of All Time. And the name is not an exaggeration. This burst released more energy in less than 1 millisecond than our entire sun emits in a full day. Think about that. 1 millisecond, less than the blink of an eye. And it outshone the sun by a factor that is almost impossible to wrap your head around. The signal was traced back to a galaxy called NGC 4141, about 130 million light-years away. And thanks to a brand new network of telescopes spanning from British Columbia all the way to West Virginia, scientists were able to pin down its origin to a region just 45 light-years across. To give you a sense of that precision, researchers described it as being able to spot a coin from 60 miles away. So we know where it came from. We still have no idea what caused it. Fast radio bursts were first discovered back in 2007, and since then, thousands of them have been detected from across the cosmos. Some repeat, some do not. Some come from galaxies packed with young newborn stars. But in early 2025, one was traced to the outskirts of an ancient, dead galaxy where stars stopped forming billions of years ago. That completely shattered one of the leading theories about what causes them. The best current hypothesis is that they come from magnetars, which are a type of neutron star with magnetic fields so powerful they would erase your credit card from halfway to the moon. But even that does not fully explain the wildly different behaviors we keep observing. Some bursts happen once and never again. Others pulse on a strict schedule every 16 days. The same source was monitored every single day for 7 years by the Canadian telescope, detecting nothing, then suddenly unleashed one of the most powerful events ever recorded. Scientists have genuinely said it best themselves. These things are ubiquitous, and yet their true nature remains largely unknown. 1 millisecond, 1 billion light-year journey, no explanation. Moving on. There is a war happening in cosmology right now, and the battlefield is a number. That number is the Hubble constant. It measures how fast the universe is expanding. And depending on how you measure it, you get two completely different answers. When scientists look at the early universe, at the ancient light left over from the Big Bang itself, they calculate the expansion rate to be about 67 kilometers per second per megaparsec. When scientists look at the nearby universe using distant exploding stars as measuring sticks, they get 73 kilometers per second per megaparsec. 6 kilometers per second difference. That sounds tiny, It is not. It is catastrophic, because both measurements are among the most precise in the history of science. The James Webb Space Telescope confirmed the local measurement to a level of accuracy within 1%. The Atacama Cosmology Telescope confirmed the early universe measurement. Both sides checked their homework again and again and again. The numbers still do not match. This is now being called not just the Hubble tension, but the Hubble crisis. And in March 2026, a major new analysis published in the Astrophysical Journal confirmed that the discrepancy has not gone away. They tested 5 different models of the universe and concluded that current data is simply not sufficient to explain what is happening. Here is why this keeps physicists awake at night. If both measurements are correct, and all evidence suggests they are, then something is fundamentally wrong with our model of the universe. Either our understanding of the early universe is broken, or our understanding of how the universe expands today is broken, or there is some entirely unknown piece of physics that we have not even imagined yet. And it gets stranger. Recent data from the Dark Energy Spectroscopic Instrument, a telescope that tracked 15 million galaxies to reconstruct the history of cosmic expansion, suggests that dark energy itself may be changing over time. Dark energy is the mysterious force that makes up 68% of everything in existence and drives the universe to expand faster and faster. We still do not know what it is. We just know it is there because of what it does. And now it appears it might be evolving. The problem is, when scientists try to adjust dark energy to fix one part of the crisis, it makes the other part worse. There is a phrase from Duke University physicist Dan Skolnick that sums this up perfectly. He said that when there is one problem, you can rule it out as a mistake. When there is a second thing, you start to think something weird is going on. Something weird is definitely going on. 68% of the universe is made of something we cannot explain. And that something appears to be behaving differently than we thought. The entire standard model of cosmology, the framework that has guided our understanding of the universe for decades, may need to be rewritten from scratch. Now let us come back down to Earth. Because some of the most baffling mysteries in science are not out there in space, they are right here, inside you. Right now, as you process this video, something is happening in your brain that no scientist can explain. You are experiencing something called consciousness. And that experience, the fact that there is something it feels like to be you. Watching this, having thoughts, noticing colors and sounds, is one of the deepest unsolved problems in all of science. Philosophers call it the hard problem of consciousness. Here is what makes it so hard. Scientists can track the electrical impulses that fire when you see the color red. They can map the exact neurons that activate when you feel pain or hear music. They can watch the brain in real time and identify which regions respond to almost anything. But none of that explains why you experience it, why there is a felt sense of redness or warmth or music, why it feels like something to be alive. We know the brain processes information. We cannot explain why that processing produces an inner world of subjective experience, and no theory currently on the table comes close to bridging that gap. Some neuroscientists think consciousness will eventually be explained by brain chemistry. Others think we may be missing something so fundamental that our current science cannot even frame the question correctly. And here's the part that makes this even stranger. Every experience you have ever had, every memory, every feeling of joy or sadness or wonder exists inside this unexplained phenomenon. The greatest mystery in science is not somewhere out there in the galaxy. It is behind your eyes. Here is something that will make your brain do something it cannot explain even further. Imagine you go to a doctor. They give you a pill. They tell you it will help with your pain. The pain reduces significantly. Real, measurable change. Real brain chemistry shifting. Then you find out the pill was made of sugar. It contained no medicine whatsoever. This is the placebo effect. And the fact that it works as reliably and as powerfully as it does is, in the words of a major review in the New England Journal of Medicine in 2025, an untapped window into the mind-body connection that defies simple chemical explanation. When a person takes a placebo believing it is real medicine, their brain can release actual potent natural painkillers. Their body can release adrenaline. Blood pressure can drop. Symptoms of conditions like irritable bowel syndrome, depression, and even Parkinson's disease have been measurably improved by sugar pills. And the mechanism is completely unknown. What we do know is that the effect has been getting stronger over time in clinical trials, particularly in the United States, making it harder and harder to test whether new drugs actually work. Some researchers believe the ritual of receiving medicine is itself doing something profound to the body, triggering cascades of chemistry based purely on expectation. The belief is doing the healing, and science cannot tell you how. Now, for something that is hard to explain to people because it sounds made up, but it is very real, there is a hum, not music, not machinery. A low, persistent, throbbing hum that has been heard by a small but growing number of people all over the world, from the southwest of England to the deserts of New Mexico, and in parts of Canada, Australia, and beyond. Sufferers describe it as similar to a diesel engine idling just out of sight. It is almost always heard indoors. It rarely registers on standard audio equipment. It keeps people awake. It causes headaches and anxiety, and in some cases has driven people to the point of mental breakdown. Researchers have investigated this across multiple countries and decades. They have suggested methane hydrate activity under the sea floor. They have looked at very low-frequency military communication signals. They have studied industrial equipment and seismic activity. No single explanation has ever been confirmed. In 2025, the phenomenon was flagged again in scientific literature as an ongoing, unresolved mystery, with new reports emerging from multiple continents. Most people cannot hear it at all. Those who can hear it cannot unhear it, and nobody knows why. So what does all of this mean? We began this journey with a signal brighter than anything ever recorded from across the galaxy. We traveled to a crisis in cosmology that is threatening to overturn our entire model of the universe. We came home to find that 68% of everything that exists is an unknown force with unknown behavior. And then we discovered that the experience of watching this video, the felt sense of it, the awareness you have right now, is something science genuinely cannot explain. Here's the thing that separates science from everything else. Science is the only system of knowledge that actively celebrates finding out it is wrong. Every one of these mysteries is not a failure. It is a door, and the door is open. The Hubble crisis will either confirm that our best model of the universe needs updating, or it will reveal something about the cosmos so unexpected it rewrites textbooks. Fast radio bursts are already being used as probes to map the invisible gas between galaxies, revealing the large-scale structure of space itself. The study of consciousness is pushing neuroscience and philosophy closer together than they have ever been. And the placebo effect is quietly revolutionizing how we understand the relationship between thought and biology. The universe is far stranger, far more vast, and far more mysterious than anything our species has ever imagined. And somehow, impossibly, we are the part of it that gets to ask the questions. That, if nothing else, is extraordinary. Thank you for watching. If this left your brain buzzing in the best possible way, subscribe and come back next time, because there is so much more where this came from.